Hey robot makers, hope you're having a good day so far. So have you heard about the Inventor 2040W? I have one right here. This is the new board from Pimoroni. Let's use it to create an updated SMARS robot and give it some much needed upgrades. So let's dive straight in. My name's Kevin, come with me as we build robots, bring them to life with code and have a whole load of fun along the way. Okay, I'm getting a bit of a warning on my live stream thing here saying your resolution's too high. I think that's because I was doing some other video work during the week and I hadn't set it down. So if it starts to glitch or anything like that, let me know. Okay, let's get over to the show. So yes, this is all about the Inventor 2040 and building a SMARS robot. So we're going to have a quick look at what is SMARS. I have a whole collection of them here. I started smarsfan.com, as you may or may not know. We're going to have a look at the Inventor 2040W as well. We have one of the inventors of the Inventor 2040 on the show as well. We're going to have a look at some of the 3D design stuff I've done to tweak the chassis and some of the other parts to make this just right for the Inventor 2040W board. And we're going to have a look at the other parts of the electronics and wire them all up. We're then going to have a look at some of the MicroPython code. And this is a work in progress, so I'm going to show you a couple of things today. And we're going to present some of the readings from the rangefinder, the laser, time of flight laser. I think it's a VL53L1X sensor, a breakout board. And we're going to read some of those readings. We're going to present them via an API on the website, which is hosted by the Pico W, which is aboard the Inventor 2040. We're then going to access that on a web page that it's hosting using jQuery to get some real-time updates and present them in a nice sort of bar. Hopefully all will go to plan during the live stream, because if anything can happen, this is live. And if you're hanging around for the live stream as well, then you can stay around for some Q&A at the end of the session too. So let's have a look at what this is all about. So what is SMARS? So SMARS is the little friendly robot that you can print yourself and learn to code. And originally it was based on the Arduino. I've got one here. This is the Arduino Uno version 3. I think this is actually a clone of that. And this is one of the very, very popular boards. This is what got me started in practical computing. It's a very, very basic microcontroller, 8-bit. And you pair this with a shield, as they call it, because it sits on top of the Arduino like so. And this gives it some extra functionality, such as it's got a buzzer on board. It has the headers pass through, but it also has some what they call terminals for the motors to connect to, and somewhere to put some additional power in, because motors are really, really hungry on power. So you can power this by a 9-volt battery. So the original SMARS robot, if I just grab one of them here, for example, I think this is a version 4 chassis in there. I can tell that because it's got 4 motors inside, but they're all based on the same kind of chassis. It's very, very similar design. Some of my most early videos on the channel were all about how to create this using Fusion 360 and then print it yourself. So yes, originally powered by the Arduino Uno, 3D printed completely, and one of the novel things I like about this is the wheels are 3D printed, along with the tracks and the pivots that hold all the track together. It's just 3D printed filaments. Really, really innovative design by a guy called Kevin Thomas. You're going to check out Kevin Thomas. I did an interview with him a couple of years ago on my website, smarsfan.com. So you click on there, go to About, you'll learn all about that. The other thing, so I've talked about the motor shield. So this is the official Arduino motor shield I have just here. So that's what, oh, this is actually, sorry, the Deke robot shield. It looks very similar to the official one. I think I've got that on another robot somewhere. I have so many SMARS robots. So yes, that provides all the functionality for driving the motors. The motors themselves on the original SMARS were these N20, I think they're like 50-to-1 ratio, which is very similar to the motors which are used on the new SMARS, the SMARS Inventor, which are these nice Pimoroni micro metal motor gears with encoders. So it has a little encoder on the back. We covered these in a show a while ago, but we'll have a look at these as well. And then the other thing about the original one is it had a ultrasonic rangefinder, which gives it kind of its distinctive face at the front, these sort of 2 eyes. There are one's a microphone and one's a speaker, and they send out some ultrasonic sound waves, bounce off an object and listen to it back. And the distance between the object and the thing that's sending it out, if you have that, you get the actual real distance. Very similar how a time of flight works, that just uses light instead. So yes, powered by a 9-volt battery, so the 9-volt battery normally sits in this sort of compartment underneath there. And some of the challenges with the original SMARS robot is 9-volt batteries, they're quite hard to come across ones which are rechargeable. So you typically use like one of these, I've got an Amazon Basics one there. Once you've used it, you would throw that away, which is not really great for the environment. You can get rechargeable ones. I have some over the corner of my room there. But they don't tend to hold the charge very well. They don't seem to handle that high load particularly well, and the motors do take a bit of a beating there. Some of the other challenges was there was no on-off button on the original SMARS, so there's no way to switch it off. You have to just like take one of the wires out of the terminal or solder a button in line with the wires. And it was also using Arduino C, and Arduino, if you've ever looked at the language, it's C++ like, but it's not true C++. It's actually based on a language called processing, and that's where you get the terms like script from. Sorry, sketch, because it was actually designed for artists to use, so they could just sort of throw a sketch together, try something out. We did a show about Arduinos quite a while ago. That was one of the pieces of trivia that came up about that. So that's the original SMARS robot. Had loads of different variations of that. You could get things like I've got a truck thing here at the front, and it's got a little servo motor, so you could put that on the front of your SMARS and control it with some additional code and a servo there, if you had a servo header on your motor shield. So the Inventor 2040, let's talk a bit more about this, because this is an amazing new board from Pimoroni. So it has the Raspberry Pi Pico board, so the Pico W, which means it's got the Wi-Fi chip on board, so that's 2.4 gigahertz Wi-Fi. And it has two Jst Ph connectors for attaching the motors. So these are the 6-pin variety, one left and one right, and that means that we can plug in our motors with the encoders on board directly to the board. So we don't need an additional board on top. Everything is on this one single board, which is what I absolutely love. So the motor driver on there is a dual H-bridge motor driver, the RV8833, and it has a half an amp motor current limiting per motor. Make sure I've got that right. Correct me if I'm wrong, Chris, or Sandy, at any point. The other cool thing that it has is per directional indicator LED. So on the where the motor connectors are here, I'll just show you this a bit closer on the screen there. There's actually two LEDs right under the word motor. You can see there. So I just sort of point there-ish. You can actually see there's two LEDs, and whether the motor is going forwards or backwards, those LEDs will indicate which direction it's going. That's really useful if you're sort of debugging code, and it also looks pretty cool as well. The other cool thing is it has 2 pins for connecting a speaker on board as well. So if you have one of these tiny little speakers, you can plug that in there. If I get this the right way around, let's see, which way does it go? Is it that way or is it that way? I think it's that way. There we go. And we have a speaker attached, so we can do really cool sound things with this as well. So we can make it beep and play tunes and all kind of stuff. I've got some of that ready to go on the demo in a little bit. One of the best features for me, and it seems like a trivial thing, but it has the Jst Ph Battery Connector on there. So you can plug in a LiPo battery, such as the Gallium battery, which I have ready to go here. So we can plug this in. I plug that in there, and I don't think this battery is actually charged up, but that's fine on this particular one because we're not going to actually use it. But yes, we can plug a battery in as well, which means again we don't need additional things to give us power. We can just use that, and that's great that we can use LiPo batteries on there as well. We've got all the protection that we need. The other thing it has is it has 6 sets of headers for the 3-pin servo. So I was talking before about, for example, this this truck thing that we can put on the front, digger thing. We can actually plug that into one of the servo headers, and that means, you know, we've got another 5 to go out. We've got absolutely loads of servo headers. I was actually hard pushed to find one of the original motor shields that had servo headers on there. The one he picks up, I don't think that's actually got servo header pins on there. But yeah, there's 6 is like absolutely loads there. And then the other side, we've got another 6 pair of header pins, and that's for just general GPIO, 3 of which are ADC compatible, so we can do all kinds of analog reading in as well. They've also got LEDs next to them, so we've got 12 addressable RGB LEDs, or neopixels, which are amazing. Again, got some code we can try out with that. We can do something really clever using MicroPython threads, so we can get our LEDs to flash at the same time as running some other code. I'll show you how to do that. It's really, really simple. And one of the most requested features on these boards is a reset button. So we can actually reset this without having to do anything. The original Pico or Pico W doesn't have a reset button on it, it just has the user button. So actually having a reset button is really handy, particularly if you're running code and you're having to sort of reset it. I must have hit this reset button a couple of thousand times during the week as I was coding this. You've also got the two Quest connectors. So at the very top end, well, the bottom end there, we've got these two grey Quest connectors. So they're the QT stemmer connectors. We can connect all kinds of other sensors and things to them as well. So that's great for expandability in the future, something that we didn't have on the Arduino. And it's generally like I2C breakout garden type stuff we can plug into that, as well as the whole Quest ecosystem. And we've got some unpopulated headers for the breakout garden as well. So the very top, very bottom, sorry, just there, we have a whole bunch of connectors. So we can connect up a breakout garden. And on the robot I've actually built, I've got the breakout garden connector plugged in there, and we have the range finding module plugged in as well. So we'll have a look at that shortly. Okay, so that's the Inventor 2040. There's so much to talk about that. Could have a show just on that particular board, but I thought I would use it in some project to sort of show some of the things we can do. Before we get to that, I just want to give you an update on some of the changes I've had to make to the SMARS chassis to make it accommodate the Inventor 2040W. So, like I said, one of the great things about the Inventor 2040W is that we can use LiPo batteries, we can use chargers, we can do all that kind of stuff. So what I've done with the first thing is I've included an Amigo Pro, which is the LiPo Amigo Pro, which I've got one of these here. So LiPo Amigo Pro enables us to plug in a battery, put it that way up, and a device, and we can charge using this USB-C connector at the same time that we're using this. So we can charge it. If we remove the charger, it's still got power from the battery, and it can intelligently switch between the two. So the first thing I did was I wanted to put this in here and have a breakout so that we can break out a hole in the side so we can actually charge it using the LiPo Amigo Pro. So that means we can charge the battery that's on board. We never really need to access that battery again. It's sort of safe in the insides of the robot. I've decided to use the gallium battery. So this is another Pimoroni product, not sponsored on this particular video. So this is a gallium battery. So it's 400 milliamp hours and 3.7 volts or 4.2 when it's charged maximum. Really nice size. It's got the hard case, so it's pretty protecting the LiPo battery that's inside. So just in case anything happens to it, it's got that nice shell protecting it from that. We've got that high quality speaker, which we looked at a second ago, which is this little speaker here. And I've also put on here, let me just grab this time of flight sensor. So let me just hold this up and show you that. So this is the VL531LX, and it's a distance sensor, can detect between 4 and 400 centimeters, and it's 5 volts. And if I show you that, that's the front end. And that little thing that's just underneath my finger there, that's the actual sensor itself. So it's got one that sort of shines the light out and one that detects it. And it's got the usual kind of breakout garden connectors, meaning it's very simple for us to just plop into the connector. No soldering required, just some code. We'll get onto that in a second or two. And the encoders on each of the motors mean that we can get some really accurate positioning feedback to where the motors actually are. So again, if I just go show you this closer there, we've got this little wheel at the back there, and that will spin round as the spindle spins round, and that means we can count exactly how many times that spindle's gone round. So we've got really accurate counts of the how many times the wheels turn round, where the position of the wheel is, and so on. Something that the SMARS robot never had. Means we can get really accurate. So yes, pew pew lasers, as Sandy says. And of course we have wireless control via the self-hosted website. So what I've done on here, similar to what I did with the Billy Bass Fish, you can host a website using the Pico, which means I can pull out this cable, have this completely unconnected to anything, and it can send all the data from the laser rangefinder onto its own self-hosted website, and we can log on to that and we can see what's going on there in real time, which is pretty cool. So I'm just going to leave that charge in there just so we've got plenty of charge for the show. Just leave that plugged in. So let's take a look at some of the actual things I've had to do to change the chassis. So the first thing is I've put some mounting points on the bottom of the board, and that's so that I can put the LiPo Amigo Pro kind of upside down so that the USB connector is pointing out and the battery connectors are sort of inside the chassis. I've put a hole there so that the on the side where the USB connector is, the USB-C connector, it sort of punches out the side of the chassis, and it also means that when we've got the tracks or the wheels connected, we've still got somewhere to actually plug this in. No problems there. So I've talked about the mounting points as well, and there is a hole in the bottom as well so that we can turn this on and off. So if I just unplug this and I just show you the bottom of the robot there, you can see a little LED that's just on the LiPo. If I just turn this around and press that, and I'll turn that off. Now I could 3D print a button and just run out of time there, just to do what I've just done there, which is just turn that thing on or off. Okay, so let's just leave that plugged in and charging. So that's the first layer. The second layer is the Amigo Pro, so that mounts, as I say, sort of upside down, and I've used some of these tiny little M2 bolts. See if I can get that to display. There we go. These tiny little bolts. They've got like a little hexagonal head on them. I use my iFixit kit to put that in place, and there's just 3 holes in there to screw into place, so I can just screw that in and it's nice and secure. And this means it can charge while the robot is running, so this is really great. It means we've got no downtime, we can carry this thing on. It's got the 2 Jst Ph connectors, one for the battery and one for the device. It's as simple as that. It has an on-off button. What more could you ask for? That's why it's flipped over and it's not the other way up, just so we can easily access that button just through the bottom of the SMARS robot. So the micro metal motor encoders, or MME, MME motor seems a bit redundant because I'm saying motor twice there, but that's what they are. These are the 50:1 ratio motors with the encoder feedbacks, which I've just shown you, and the 3D model uses these regular ones just so that that I had to hand in Fusion 360 just when I was modelling this out. So one of the things I do need to do on this model is just model a little shim to make sure that motor is pushed up and raised the correct level, because when I've been playing around with this, they do rattle around a little bit, and I need to make sure that they're really solidly in place. And you just hear that the encoder sometimes hit the chassis inside, and that's not good. That's not what we want to happen. So there's just a little bit of extra work that I need to do there, just to create like a little shim that goes in and just lifts it into place and secures it nicely. But I have got 2 mounting holes you can see there, which is to secure the next layer, which is the battery holder layer. So I have a earlier prototype just here. So the idea of this is we've got somewhere to put the battery. So in this little corner here, we can, in fact it's that way around, we can put the battery in, and that can go through the hole in the bottom, so we can easily access things that we need to there. And also if we get the LiPo Pro, in fact if I go to the overhead, I'll probably show you this a bit better. So I've got the layer here. This is the LiPo Pro, LiPo Amigo Pro. And what I'm going to do is just connect the device to this first one. I'm then going to connect the battery to the second one. You can see there that's switched on. See there's the LED, and if I press that, that'll go off. So that can go upside down. And then inside the chassis, we can put the battery through, and that can just sit there like so. So it's kind of like in that orientation inside. Just like so. And then this wire here is the wire that will go to the Inventor 2040, which is here. So that can go plug into that connector like so. Get that in there. Might be a bit easier to just do that. There we go. So that's kind of the electronic makeup of this thing. And that will sit on the next layer, and then that's sort of underneath there. Does that make sense? Like so. So that's what's going on just inside that robot there. That's what the layers look like. That's how it all wires together, so pretty simple. And that's the thing that allows it to connect. Now you can see the 2 mounting holes there and there. And we've also got these other 3 mounting holes for the Inventor. So this can sit on there, and again we can use those little bolts to sort of hold that in place. So on this earlier one, I actually did the mounting holes the wrong size. I think these are 2.5 instead of 2, so that means that they don't actually stay in place. But on the new one, they are absolutely in place there. Okay, let's get back over to our keynote. So yes, holds the motors in place, holds the gallium battery in place nicely, provides mounting points for the Inventor 2040W, and it's all friction fit, so it just pops inside, doesn't need any additional screws really. I've not got screws in the final model in the middle bit to attach it to the chassis. It just sits in there and there's no issue there. So very simple. We can attach with the M2 screws if we wish. So then we've got the gallium battery, which I've just shown you sitting in place. That's that 400 milliamp hour hard case LiPo battery, 3.7 volts nominal voltage, which is kind of what it operates on normally, but when it's fully charged you get 4.2. Now the great thing with the Amigo board is it'll just sort of flatten any of that out for you, so it's fine. And it has those two Jst Ph connections as well, and I've got the lead, which is I've just shown you in there. Let me just find that. So this cable, which goes from the LiPo to the Inventor 2040, is just a standard Jst Ph to Jst Ph. I just heard something fall on the floor there. Oh, it's the screw. That's fine. Won't be in my show if I didn't drop something during the live stream. And it's got short circuit protection as well, and that's nothing to do with the film Short Circuit and Johnny. This is to do with just getting the polarity wrong or shorting the wires out and so on. Protects against all that kind of stuff. Works perfectly with the Amigo Pro as well. And the speaker holder. So at the very front of the robot, I've got this sort of oval shaped hole and this thing that fits into place there, and this holds a little mini speaker in place. Now the mini speakers I've got really short cables. I bought these before the Inventor 2040 came out, so they do want ones with a slightly longer cable on them. I think it's 6 millimeters instead of 6 centimeters instead of 1 centimeter. But this one actually fits fine. We can get sound out of it. It's just a bit of a tight fit just in the corner there. But the idea is this just holds the speaker in place, just slots in, no screws or anything required. Completely optional, you don't have to have that. Kind of gives this a similar kind of look to the original SMARS robot. If I just grab one, put this next to it, you can see they've kind of got a similar kind of look then. There we go. Okay, let's get on to the next one. The mini speaker itself is a mini oval speaker. The one I've got's got really short wires. It's 8 ohm 1 watt, surprisingly loud as well, I would say. MicroPython can help you do some beeps and tones. I understand, Chris, the CircuitPython version can play sound files, so you can actually do like proper sound clips that have been prepared for the Pico W, but the current build of MicroPython, or the batteries included version of Pimoroni MicroPython, they don't allow you to do sound files yet. Don't know if they ever will, but they don't currently do that. CircuitPython does. CircuitPython doesn't have Wi-Fi capability at the moment, so bit of a trade-off. So there's a bit of a smorgasbord, is that how you pronounce it, of all the different parts I've used, all from Pimoroni. So we've got the speaker at the top, we've got the two micrometal encoder motors there, we've got the LiPo charger in the middle of the Amigo Pro, we have the Inventor 2040W itself, we've got some cables which connect the motors to the Inventor 2040. These are the 6-pin JST cables. They do have short ones. This is the very long version, but they do ones that are a little bit shorter than that, which is what I've got currently in there. So they're sort of nice and tidy and really small. And we have the VL53L1X time of flight laser rangefinder, which is, I love this thing. And I mentioned the motors. We've got the Jst Ph to Jst Ph cable. That's a little cable just here, which is to connect the Inventor 2040W to the device on the LiPo Pro. The Amigo, let me get this right, the LiPo Amigo Pro. And we've just talked about those cables as well. I've gone for the 10 centimeter, 100 millimeter version, which is just seems to be the right size for my particular robot. And of course, we've got the battery as well in there. So there are all the bits and pieces. Pretty simple to put this together. They've all got connectors on them already, so there's no soldering required. I really like that aspect of it. One of the things that was really quite challenging with the SMARS robot, if I just grab one of these here, is they either use DuPont cables to connect in the headers, which result in these sort of ugly wires coming out the side, or they had wires that had to go into a terminal block and be screwed into place, but no on-off button. So if I plug this in, I think the battery's probably well flat on this one. Yeah, that's completely dead. But there's no on-off button. There's no way to charge the battery up without pulling everything out, taking all the wires out, pulling the thing back, disconnecting the holders that hold the... in fact, I can show you in here. If I go to the overhead, I can show you this a bit easier. So this is the original SMARS. I'd have to pull back the shield there. You can see the motor is in place. Sorry, the battery is in place and it's held by these motor holders. So you actually have to pull them out to get at the battery. So it's really quite a big ordeal just to change the battery. hence me not changing the battery very often in these. So that's all the electronics. And onto MicroPython. So let me see if I need to switch to another screen. I'm just going to click over to that one. So just before we switch over to the screen and show you some of the code, these are the things that I built up which are in the Git repository for this project. So I think it's SMARS_Inventor on my GitHub repository. So the first one is the index.html. So this is the web page that it will self-host. It's quite a straightforward web page with a bit of JavaScript embedded within it. We'll have a look at what that does in a minute. There's music.py, which plays some nice nautical themed music. We have silence.py, which stops the speaker. This is because I had I think the SMARS Inventor, which is a demo of the motors, the lights and the sound, which we'll have a look at. I had that saved as main.py. So every time I put power on, the speaker would fire up. If I had that plugged into Thonny, I would have to sort of hit the stop button to restart it, but then the note would continue playing. So I'd have to have something that says stop all notes. So that's what silence does, it just stops the music. We've then got the VL531LX.py rangefinder driver. So the story with this is this little rangefinder that's available on the Pimoroni store is compatible with Python, but there is no drivers for MicroPython. Or there wasn't until this weekend when I sort of hacked one together, and it works fine now. So I'll submit that to the guys and see if they want to put that on their product page as well. But this now works with MicroPython, which is great. I did have the other version which worked with MicroPython, which is the 0x instead of the 1x. That's the much smaller version. I've got that on the, trying to look for it, but I can't see it. The SMARS Mini, the really small SMARS robot. And yeah, I can't find that. That version is like a really small version of that. That code didn't work for some reason, so I had to find some other code, look at what the different instructions are that you have to send to the I2C bus, get them in the right sequence, and then put that in some nice class that we can then use. So that's what that does. It's a class. We can use that in our code just to get the distance. So nice and simple. And then web.py, this is the main thing I've been working on this weekend, and that's the self-hosted web server, which allows us to connect to our robot. We can see what the current rangefinder distance is, and we can interactively get readings back from that. It's really cool, and it uses a few different layers of software to do that. So the first thing it does, it uses the rangefinder driver just to get the distance. It then presents that via the web hosting layer, so it provides like an API, so you can get that reading whenever you want. And then I've got some jQuery, which is JavaScript code running on the self-hosted web page, which really is, run from your browser, that then asks that API what's the current distance that's being read in, and then it will then put that inside the page, updates it without you having to refresh your browser, and then I put that into a Bootstrap progress bar, so you get a nice little interactive progress bar / rangefind bar. Really, really cool. So we'll have a look at that too. Okay, I'm just going to have a quick sip of my drink there. So if you like what I do and you want to help me out, you can give this video a like, whether you're on Facebook or YouTube or Twitch or Twitter. You can drop me a comment, tell me if you've checked out the Inventor 2040W yet, whether you're going to get one yourself. And if you've not already subscribed to the YouTube channel, please hit that bell, give me a subscribe on the channel. It really, really helps grow the channel, and share this with other people. And I do go live every single Sunday at 7 o'clock. British local time, whether that might be. So currently we're GMT +1 because we're still in summertime, but I think in the end of August, October-ish, that's when it goes back to GMT, whenever daylight savings is over, or British summertime as we call it. Right, demo time. So let me just get myself sorted here. I need to disconnect that, connect that up. What I'm going to do is I'm going to connect this cable here with the robot, and I'm going to plug it into what I'm going to do first of all is just switch it off. I just need to get to that button at the bottom and switch it back on. There we go. I'm just going to plug it into the Pico W so I can program it. And a bit of a flaw in the design here. When I designed the speaker holder, I didn't really allow enough space for that to go through, and this is quite a particularly chunky Amazon Basics micro USB cable, so I've had to just unscrew the screws a little bit just to allow it somewhere to plug in there. But yeah, it's a bit of a tight fit, that. Okay, so what I'm going to do is just move some of these other bits out of the way, so I've got a bit more space to play on in the middle there. And let's go over to here, And let me just load up Thonny, which is over here. Right, so let me just shrink this down a bit so we can see everything at the same time. Okay, and let's stretch that out there. Right, so I'm just going to hit stop. Excuse me. Right, so we've got on here now, just check out the version of MicroPython that we've got on here. I'm having a few issues with this version, this build of MicroPython, simply because I think it's quite an early release. So 7th of July is when this particular one was released, and this is the batteries included Pimoroni MicroPython build. I say I had a few issues. I just had to restart it a few times when I'm doing stuff to do with web pages. That probably is more to do with the driver, the Wi-Fi driver. I think when you get the network driver to do something and you reset your Pico W, it doesn't always reset properly. So sometimes it just hangs. Right, so we've got our robot there in the middle. What I'm going to do is I'm going to load up some of the, let's try the music one first of all, and I'll move the microphone across so you can hear what I can hear. It is pretty loud anyway, so let's just load up that. And let me just move this down. I'll just tell you what this code actually does. So it's reading in the Pimoroni reverse direction, which is to do with the motor direction, because I'm going to use some of the motors in here too. It also brings in the Inventor, which has the Inventor 2040, the number of LEDs, motor A and motor B. And Chris will probably think, why is this in music.py? But it's because I merged all three things together in here. We've then got some nautical music, and we've got a whole list of tones. So each one of these tones has got a frequency, and we use them to build up a piece of music shortly. Let's notice my lights just changed colour then, which is weird. Okay, and then there's the song itself, so that's the sequence of them, so we can do a quick lookup for each of them to get the frequency and to figure out. And the note duration, so if we've got a note that we play many times, we just have that in the same number, so there's no pause thing in there. We then initiate the board from the Inventor 2040W class. We then initiate the motor A. Because I've got these, let me just grab my SMARS thing again. Because on my SMARS robot, I'll just grab two motors. If I have motor A in there and I have motor B in there, they're actually facing in opposite directions. So when one's spinning round, the other one has to spin in the opposite direction to make them move in the same direction, if that makes sense. So what I've done is just arbitrarily reverse the direction of motor A, which I can't remember if that's left or right, but it doesn't really matter in this particular case. Board volume, interestingly, that's set to quarter strength. So one would be like the full volume, 0 be no volume, so quarter strength because it's pretty loud. And I have got the speaker plugged in there as well. We then got the user button, so we can toggle the user button on or off. So the user button is next to the reset button just here. And that means we can press that and it'll trigger either stop the music or start the music. So we've got this little check toggle button piece of code there that just checks whatever the last state was and toggles it. Returns what the state is. We then got some brightness. This is for the onboard 12 RGB LEDs. We can do some really funky stuff with that. And I've got a piece of code here which is just LED test, which will just test all of the LEDs. It basically just changes the hue of each of them each time it goes around the loop. And we can fiddle with things like how often it does that, what the speed is, how many updates per second it does, and so on. Then got another piece of code which tests the motors, and it will basically just go through each of the motors, enable them. It will then make them go full negative, which I think when I was running this was forwards, which is fine, and then stop to stop the motors. And then the other thing I do is I use the threads. Now, if you remember when we did a piece of code, we did a show on MicroPython threads. The Raspberry Pi Pico W has 2 cores, so you can run 2 MicroPython pieces of code at the same time. And the way that we do that is we use the threads library. So _thread, start new thread, LED test will run that LED test code that we've got up there, which will cycle through all the colours. And then it will basically just carry on the piece of code then. So it'll then go while true, do the motor test, check if the button's toggled, play the music, otherwise stop. And it'll do that, and it'll basically just keep playing the music round and round. So what I'm going to do, I'm just going to just hold on to this so it doesn't run off the table. I'll just hold it like so, and then let's press play. So that horrible zzz, zzz, zzz. Can you hear this? Yeah, that sound is the motors. There we go. Basically just not being in the right position. I don't know if you could hear me say that then. Yeah, that horrible scratchy sound was just the encoder just hitting the bottom or the top of the layers, and that's why I just need to put that little shim in place. But you can see there they're spinning around and then stopping dead, and we've got the LEDs sort of cycling through there, all the different colours, and that's 2 pieces of code running simultaneously. So I love that about Threads, and it'll keep doing that. Let's just press that user button and it'll play that music again. Can you hear that? There we go. And it'll keep doing that. And I'll press the stop button, I think, again. It'll keep going around. So I'm just going to press stop on there, just to stop it. There we go. So the code's now stopped. You can see the LEDs are sort of frozen where they were. So that's music. Let's try... I'll just show you the laser rangefinder stuff, because this was just like to put together. So we basically just have to build up a configuration, and it's every single byte that we need to send to the I2C bus, and there's like loads and loads of ones that don't really do anything. And let's do that, and then we build up a class that basically just brings in an I2C. We then reset the rangefinder so that we know it's in a good state. And have you heard of this before? Machine.lightSleep. So machine.lightSleep will basically put the machine, it's a bit like a sleep function in Python really, but it does it at a hardware level. So it'll sleep for a second, but it keeps everything in RAM. It doesn't actually do anything other than just sleep for how many seconds that you provide. If you did deep sleep, it actually goes to deep sleep. It will switch off all the functions on the board and use very, very low power. But when it wakes up, it's as if it's just done a hardware reset. But there is a little flag that tells it whether it's done a deep sleep or whether it was actually a hard reset that's been performed. So you can just check whether it's been asleep or not. But you do have to load the program up again, essentially. So then we check to see, you know, I've got the right ID model for the rangefinder. We then bang a load of bits into the to the I2C memory bus. We then do another light sleep just to make sure it's actually taken them. So I think they're milliseconds instead of seconds, actually. And then we've got a whole bunch of features like writing registers, writing 16-bit registers, reading 16-bit registers. A lot of them are actually not used, but just there for completeness. And then I've just put there the property, which just means you can read that model ID without having to have the brackets on it. So it's nice, cleaner code. We've got the reset function, which just writes 00 to that particular memory address, does a light sleep, and then writes 1 to that memory address, and that makes it just a reset. And then the main function, which is read, which gives us our actual distance. So we can say data equals self to I2C, read from memory. We get that particular memory address there, 89. We pass in 17 and the address size 16 bits, and then we just correct it for crosstalk as well, just to correct it, and then we just return that. And because that's a read and I thought that's a little bit ugly, let's just give it a property which is distance. So there we go. Okay, so question just there on the chat, which was, does CircuitPython support threads? And we don't think it does. I don't know if Anne Barella is on the chat or whether she's seen this as well, but you can probably vouch for whether it is or is not covered by that as well. Did I say her name correctly there? I always think of Barbarella when I see a name. Totally random. Okay, so that's the driver that we use, and let's have a look at SMARS Inventor next. Okay, so what did I do with this one? We just have a quick read through the code because I think I might have since improved this one. Yeah, so that was basically just what was in that music.py. There we go. Okay, so what I'm going to do now is load up the web.py, and I'm going to get a browser loaded now. I did find that it would take about 90 seconds sometimes for it to properly connect, and I don't know whether that's to do with like a DNS, DHCP or other problem, or whether it's just something to do with the code that I'm running. I don't know, but it just took, it seems to be random. Sometimes it connects instantly, sometimes it takes a couple of seconds to connect. So I'm going to run that. So this time the robot's not going to move anywhere. It's not going to do anything visible. The LEDs are not going to change, but it will read the rangefinder and it will report some things out into the console. So let's just run this and see what happens next. You can see the onboard LEDs flashing, and we're getting some heartbeats. I've just set the distance to 0 because I found that when I was taking readings and having this in this particular loop, that was making it have some problems. I can also see what IP address it is as well. So I'm just going to go back to me for a second while I just load up a browser with that IP address there. So .84, and we'll talk about how this actually works. Actually, worked first time. So let's go back over there. Right, so I've now got, if I actually go over to here and bring this down so you can see it. So SMARS Inventor, this is an example web page for your Pico web server, and it's got a bar there. Now, as I move my hand back or move it forwards, you can see that that bar is changing in length, and it's pretty quick to update. I think I'm doing this about twice a second, so like half a second for refresh, and it seems to be quite accurate distance wise. I was just going to get I've got a ruler to hand. We can see if this is an accurate measurement. There we go. I have one just here. So if I put this this way round, about 10 centimeters from what I think is the center there. If I put my hand there, about there, that's 10 centimeters, so it's pretty accurate. Let's go to about 5. Yep, so it looks pretty accurate to me. So that's 7. So it's working pretty fine there. And I've got some other bits and pieces in front of it there, so if I try and move them out of the way, we'll get like what the largest distance, if I just fire it off over there somewhere. Let's see, because it did say it's between 4 centimeters and 400, and I'm getting a bit, I mean, this room is actually only 3 meters, so that's probably about right actually. So yeah, how cool is that? So there's quite a lot of things going on there. If I go to the 1.84 and I do /distance, which is the API, we should get, if it decides to update that, and this is where sometimes it can, because we're getting, maybe I just need to close that window down, and let's load up 84 again, /distance. I might even need to reset it there. One of the reasons it seems to do this is it can only really have like 1 or 2 connections simultaneously. It is a Pico, it isn't particularly high powered. There we go. So I've got the reading there. The distance is 51 and the percentage is 95. And all I've done there is just taken, I think it was 2,600 millimeters, and then divided whatever the reading is by that to get a percentage, I think, and then just halve that. So this isn't real time on this one. You have to press refresh to get a different distance, like so. Let's see if that's going to update. Seems to have frozen there, but it's still flashing the LED, so that's that tells me it's working. There we go, distance 47, and that's what's happening in the background when we. So let's go to the code and have a look what's going on there. Right, so like I said, there's quite a lot going on here, bear with me. So we have network, we have secret, which has got the SSID and password for the Wi-Fi. We have machine, we have pin, the watchdog timer. I don't think I've got that enabled currently on this code, but whenever we're doing anything which is like web servers and we want it to run a long time, it's probably best to have something like a watchdog timer in, and I did a short video about that, the one with my little dog Archie on the front as a thumbnail. We have UAsync IO and Async IO coming in. This is because we want to do things instantaneously as they come in through the network port, and we can use that. Socket is for all our network connectivity, HTTP type stuff. We've got the rangefinder driver that I wrote myself. We have the Inventor 2040 there, and we've got some JSON because I output that to the API using JSON. So that's what that helps us with. So what I then do is I bring in the breakout garden pins. I'm not sure if that's the right way to do it, Chris, or if there's a better way now, but that's, I think actually I don't need them anymore. I was using some code. I think that can probably disappear because board.I2C has the right pins, doesn't it? So we don't need to use that. So we've got board, which represents the Inventor 2040. We've got the sensor, which represents the time of flight laser rangefinder. And I've got the onboard LED because I want to blink that to show that there's some activity as a heartbeat. So the next piece of code, these 3 lines here, are to do with connecting to our Wi-Fi. So we just create a new WLAN variable which holds our network interface. We then activate it, we then connect to our Wi-Fi, and then we've got a bit of code that basically just says while you're connecting, just put a dot on the screen, and the end equals nothing just means print everything on the same line. Don't do it a new line. So instead of going dot 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 down, it goes dot 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 across the terminal. And then at the end, once that's finished, we just print out what the current IP address is and gateway and mask and all that kind of stuff. Then I read in the index.html read only. So I read that into a variable that's called HTML, close the file. I then grab the distance using sensor.distance. That sensor is from the laser rangefinder when we brought that in before. And then we've got a piece of code here which is called async serve client. So the asynchronous bit means we can do things like await, which means that we can do things without blocking the main piece of code. It's a bit like using threads, but it's not. It's more to do with synchronous or asynchronous behavior. So doing things in a sequence or doing things kind of out of that sequence as they occur. So we bring in the sensor, the HTML web page, the distance from the sensor. We then get another sensor reading just so that it's more up to date because we don't know when this is occurring. We then print client connected. We then get the... So what's happening here is when you go to your browser and you hit like load the page, that comes in as a request. And the request is made up of many lines. And really, we're not really interested in a lot of the headers and stuff. So this piece of code that says await reader.read line, it's basically just waiting to see this new line carriage return thing because that gets rid of all the header information that we don't really care about. The bit that we do care about then is the URL. Do we get in the URL passed to us, do we get /distance? Because if we do, we know that's an API call, and we simply just want to write out the percentage and also the distance. So the percentage, and again, this is probably not the best way of doing this, but I pass it through as a string, 100 minus, just because we want to get the 100, and then 2600, which seemed to be the maximum range when I was using this rangefinder with my own driver, divided by the sensor reading. And those two divides mean divide with an integer so that you return an integer, not a floating point number. So if you just do 1, you'll get a floating point number, because if you do 2 slashes, you'll get an integer. So that's a little tip there. We wrap it around in a string because I want that to be passed back as text. And then print that out just to the screen just because I want to know what that is. And then if the URL equals 6, meaning you have found that and it is distance, then we get two variables, one which is distance. And this is me just building up the JSON string, so I use the little squiggly brackets to make it a list. So distance equals sensor reading divided by 10, because it gives it in not millimeters, well, it's like hundreds of millimeters or something, so I just divide it by 10 to get actual millimeters, I think. And then percent equals percent that we just calculated a second ago. We then wrap that up in a response using JSON, and JSON dump string basically takes our list and makes it into text that we can then put in a string. Otherwise, if it's not /distance, if it's just like load the regular web page, then we just say the response equals HTML, and then this is an old school way of doing replacing text within our HTML file with something else, which is a variable. So that percentage is like string formatting, string replacement stuff, but it works well. I tried using some other techniques to do this, and it said that they weren't implemented yet in MicroPython, which was interesting. So we pass the sensor reading, which is just that number of millimeters, and we also pass it the percentage as well. And they get then replaced in the HTML where there is one of these percentages. So if we look at the HTML file, we'll see that within the text there is this percentage thing, and it basically just replaces that with this variable, which is pretty good, or the contents of the variable. We then write that out using the writer, which is declared above, which is passed in, which is part of our sockets. So we're basically just writing some text out, which is HTML text, passing 200 saying everything's cool, everything's good, and here's some text back. So all these /r/n is like returns and new lines. So that's just some formatting for the web page. And then we finally write out the response itself. We then wait for the writer to drain. So we imagine we've stacked it full of bytes, and because it's over a network, we have to wait until all those things have been sent, and once it's drained it, we can then close it. So we have to just await it being closed. Once it's closed, the connection to the browser, we can then just say client disconnected. Sandy says there's a library that's called TinyWeb, which is really good for this kind of web stuff on the Pico W, so I'll definitely be checking that out. I did see that in my research, but I thought I'd just go with this standard stuff that I know for now for quickness. And then we've got a function which is called main, which is kind of like our main loop, but the main loop is actually further down. Again, this is an asynchronous piece of code, so it can run at any time. We bring in the sensor, we print out setting up web service, we run this at the very beginning. We then do a synchronous IO create task. So again, it's a bit like threads in that you have to sort of create a task. We create the serve client code, which we just ran earlier. We pass it an IP address, and we pass it a port to connect to. So port 80 is standard HTML Port 443 would be like secure with a little little, what's it called, padlock. And then what I've also done is just have a little counter, and just while true, I originally had the distance in there. You can see it says distance equals sensor distance, but I found that was interfering, and I think it was because it takes an amount of time for it to get a sensor reading, like fractions of a second, but it was interfering with the loop. So I just took that out for now, just set it to 0. Onboard on is just the LED, just sets that to on. I print out what the, I set what the IP address is from WLAN IP config. I'm not sure why I'm doing that within this loop. That's a really bad piece of code because that isn't going to change, and therefore probably shouldn't be in this main loop, but I've got it in there anyway just in case. Then I just increment the count just by 1, and then I print out that line. You can just see there heartbeat, the distance, and then the IP address. And then I wait, doing a synchronous IO sleep. Because it's an asynchronous function, we can't use the regular sleep function. We have to do an asynchronous sleep, which is kind of analogous to that. And I just sleep for a quarter of a second, turn the board off, and then wait for another quarter of a second. Okay, and then the main loop. So we try asynchronous running that main loop code there. And finally, we create a new event loop. So what the event loop does is it's like having a while true, just run this same function over and over again. So that's what happens there. That's it. So that's what's going on there. Now, if you go over to the web page again, if I just go back over to here, and I load up the main page again. If I now go to Option Command and I to load up the dev tools, and we look at the actual source code itself of the page. Let's see if I can load this up from in here. I think is it elements. There we go. Right, so this is the actual web page itself. So we've got in there, and you'll actually see these things actually update. They sort of flash to say that they've been updated. So I've got these divs. Divs are like divisions in HTML. It's a way of sort of blocking out your page into different sections, and these classes are things that you can give it styles. So I'm using something called Bootstrap, which is defined in this header thing up here. So I'm just bringing in Bootstrap, which I think is there, bootstrap.bundle.min.js. Excuse me, and the one above is the actual style sheets. The JS does some JavaScript stuff on top of that. We could do things like animations and or transitions, make the bar. So instead of just like doing that, it can slide. I don't think I've actually got that enabled in there, but we could probably fiddle about with that to do that. And further down then we have the actual code of the page. So we've got this is an example web page. You can see as I highlight these, it actually changes color in the background there. So you can see that. So heading 1 is the actual header that says SMARS. Let me just move this over to the right. You can probably see it a bit better actually. So heading 1 is that piece there. The P is for paragraph. That's the paragraph tag. That's what, if you've not seen HTML before, this is what all this looks like. And then we've got 2 other divs, one for the distance and one for the progress. So the distance there, you can see that's changing in real time. So the way that that's being rewritten over and over again is because up here we have a piece of code which runs Ajax. And this is like a synchronous JavaScript extension, something or other. So this is a way of editing your web page in real time within the browser, so you don't have to keep refreshing the browser to get a new distance. It will do this for you. So this little piece of code here, function, I hate JavaScript and going to put it out there. I just find it an ugly language. It has like, you wrap things within things within things, and I just find that like a really bad approach. So this $.get will get from the /distance API which we've created, and it will it'll grab data and status. We've got an object there that's called a variable that's called object, and that's basically going to parse the data that's passed to it. And if you remember, we've got those squiggly brackets, we've got the little speech marks, it'll say distance, and then we've got the colon, and then the actual value of the distance, a comma, and then we've got the percentage, colon, and then the actual value of the percentage, and then we've got the end of the squiggly brackets. So that's what happens there. That's it parsing that data into a JavaScript object, and then it's trying to then find, so this dollar and then this in the speech marks hashtag distance is trying to find in this code. So further down you can see this ID is distance and ID is progress. It's trying to find those in the code, and then it's basically just going to overwrite what's in there with this new piece of string, which is the strong distance object.distance plus strong. So is just that millimeter there. So what's happening is that little value there is whatever's in object.distance, and that's what's being passed in and parsed through the JSON object that we're passing through from our API that we created in MicroPython. And it does the same thing again, but it does it with the percentage as well. So that's how we get the pieces of text there. And then beneath that, we've got this other thing, which is this progress bar. So progress bars are part of Bootstrap. It's essentially just a box with a color and a width, and then you can change within the Bootstrap thing what the value of this is. So if I just, can I move that out of the way? Maybe I just need to move that over. There we go. So this very long piece of code here says the ID of this tag is progress, the class is progress bar, the width is whatever the percentage is. So as I put my hand in front of this and move that down, you can see that W is changing, and that's a Bootstrap thing that basically just says change the width of the progress. The roles is a progress bar, the area label is a basic example, and the area value is now 95, and again that changes depending on the distance of the percentage that's in there. The area value minimum is 0, the area value max is 100, and that's the minimum and maximum value of our progress bar. And then the style width is the thing that's actually changing the width of the progress bar. So if I just move that down again like so, you can see as I put my hand in front of it, we're getting that sort of almost real-time updating through jQuery. So this is called jQuery, this piece of JavaScript that we've got up here. And I'm pulling in jQuery using these style sheet and script links. So you can see there code.jquery.com, jQuery 3.6.0.js, which is the JavaScript library. It pulls that in, means we don't have to host it on the Pico, similar with the Bootstrap. And that's it. So that will then rewrite these elements on the page in real time based on what the current distance is. You can see there where it's flashing the divs. We're getting the pages updated. So if I close that out, we can see that now. Why did I go to all this trouble of doing that? And it's because what I want to eventually do with my SMARS robot is have a dashboard on a web page. So if I unplug this, let's unplug this, and it's still flashing away there, as you can see, but it's not got any wire connected to it because it's completely on its battery, and hopefully it will carry on updating the page. I might have to reset it to do that though, however. Not sure why it's decided to decide at this point not to work, so I'm just going to reset that. And the way that I know that it's working is that little LED will start flashing once it's got a connection to the web. So once it starts doing that, it's like hosting its web page. And the battery should be pretty charged up. Oh, I didn't turn it back on. It's an idiot. Let me just do that again. So I've just basically just pushed a little pencil there. You can see the LEDs come on there, and within a couple of seconds you'll see that LED flashing to say that it's got a connection to the network. There we go. So if I'm curious to see, do I need to update the page? And no, I don't. There we go. So the robot is now completely unconnected to any wires. This is pure wireless, and it's hosting its own web page and giving us live feedback. So yeah, I want to have a dashboard a bit fancier than this that's got the robot there. You can see what the actual rangefinder is showing back, and then you can click different buttons either to control the robot or to set different demo programs such as avoid, obstacle avoidance, or obstacle follow, or all that kind of stuff. We could even potentially connect this up using ROS based on what the rangefinder distance is, and using the dead reckoning of the motors based on the feedback from the encoders. I could include the encoder feedback as well for the motors, whichever ones. I think that's the motor one there. But yeah, you get the idea. So I haven't actually got this running round doing stuff yet. I need to work on a few other things before I get that working right. But you can see the work in progress there. Pretty pleased with how that works. That's what I envisaged working. It does work. Cool, cool. So let me just jump back to my slides and see if there's anything else I wanted to cover off on there. I think that was pretty much it. So somebody was asking before about Discord, is it members only and so on. So if you want to join Discord, you simply have to go to action.smarsman.com/Discord, join-discord action.smarsfan.com/join-discord. I think Alex has dropped a link in the chat as well. So if you check that out, you can join for free. There's no kind of like a restriction there. We just want to keep it to people who are just passionate about robotics. That's why we've got a Discord. We do have a Facebook group, which has got like 23,000 people on there. But there's a lot of stuff on there that's like spammy and so on. And it's an endless, thankless task getting rid of all that stuff. So Discord is definitely the way to go. It's a much deeper sense of community, I think, on there. And yeah, it's the place to be. So I think that's it. Yep, there we go. And then if you want to support the show, you can do a super thanks. If you want to help out the show, you can also do things like go to the buymeacoffee.com/Kevin McAleer and buy me a coffee if you want to help out with all the stuff that it takes to run the show. So there's all kinds of things like the equipment I use to do all the overheads, all the lighting, the microphones, that kind of stuff, the streaming royalty-free music. Copyright strikes are a real thing, and we have to make sure we stay away from that by using royalty-free music, which isn't free. And graphic software for doing all the eCam stuff, which is like a monthly subscription to do the streaming, and things like Canva Pro for doing all the thumbnails and whatnot, and all the equipment and things like tools and so on as well. It's not a cheap hobby, I'll put it out there, even though I do get support occasionally from my friends at Pimoroni. If you want to check out the website, smarsfan.com, this is all about SMARS robots. This is much more targeted at the original SMARS robot, which is based on the Arduino, wherever I put it, the Arduino motor shields and so on. But it's a really great thing if you're starting out in robotics and you want quite a cheap robot to put together. Highly recommend that. You just need a 3D printer. So check out smarsfan.com. And I think that's that I wanted to cover off. I've got another button here which is like going live every Sunday, but we've already talked about that. It just shows you the different time zones around the world depending where you are. So if you're on the sort of Americas, that's on the left hand column there. We've got PST, MST and so on. If you're in the sort of European region, we've got all the Eastern European, Pakistan, we have Russia in there as well. And then on the very last column there, we've got the sort of Far East. We've got things like CST, China Standard Time, and Australia as well. So you know where you are, but you probably know what the offset is from GMT. We're pretty much GMT here in the UK. So this is the point in the video where I'll say thank you very much for watching on the replay. If you're watching live, we're going to do a Q&A chat now from the sort of 15-20 minutes. But if you're watching this on replay, this is a bit where I cut the video, and I shall see you next time. So thanks for watching.